So I'm at the ice cream shop and there's like 32 different flavors. And I want to get a triple decker cone. What are my options? We'll begin with a drawing, an illustration of the problem. We'll draw a very mathematical structure. It's a cone. Cones are very mathematical, they're geometric. And we'll toss on here. Didn't leave myself a lot of room, so this is going to be, I don't know. There's scoop number 1. There's scoop number 2, and there's scoop number 3. It's falling over. So yeah, okay. Actually, let's say that I'm worried that it's going to fall over, and so I'm going to put it all in a dish. Okay, which means order doesn't matter. Okay, if I choose vanilla, chocolate, and liver, you can pretend that's lemon if you want. That's going to be the equivalent of liver, vanilla, chocolate, or chocolate, liver, vanilla, or okay, that doesn't matter. Okay, they're all the 3 are together. So that's important. So order, I'll say order, not important. Right? But I'll tell you what is important is they all have to be different. They're all different flavors. I don't want 3 vanilla. I'm not going to go place with 32 flavors and get 3 vanilla. Okay, I might get 32 butters. Or sorry, I might get 3 butterscotch or 3 licorice. Okay, but we're going to say that order is not important, and they're all different. Okay, that's important. All right. So how many flavors do we have? I'm going to say 32 flavors, and I'm calling the number of flavors, the number of choices, 32. And in this case, where it's flavors that we're looking at. And I'm calling the number of scoops 3. Okay. So what we have here, it's a more generally, we're choosing 3 items out of a set of 32. Okay, where order doesn't matter. It's like, let's say I've got 32 unmatched socks in my drawer, and I want to choose 3 of them. For whatever reason, I would need 3 unmatched socks. Okay, so I choose 3. How many different ways could I choose those 3 socks? And when I get those 3 socks, it doesn't matter whether I chose the blue one first or the knit one, or whatever, because they're all going to go together in whatever container I need to take them to wherever I'm going to use 3 unmatched socks. Okay, let's move away from the socks. Okay, back to the ice cream. So N is the number of flavors, K is the number of scoops. How can we choose 3 scoops out of 32 flavors? We're going to introduce a notation. Okay, it's not a new idea. We've already described the idea. This is just a nice shorthand, mathematical shorthand to describe the question that we're asking. And we have a way of saying that. It's N choose K. Okay. So for example, in this case, we've got 32 choose 3. It's exactly what we're asking, and we would write that as 32, 3, 32 above 3. You do physics or other sorts of mathematics, it looks like a vector. It's not. 32 over the 3 in these parentheses, 32 choose 3. Okay. And actually, let's work out this specific example before we come up with a generalization. What are our options? Well, we've got the first scoop could be, there's 32 different ways that we can make that first scoop, isn't there? Okay. And the second scoop, there's 31 different possibilities for the second scoop. So we're going to multiply them because each of those 32 first scoops has 31 variations, you could say. And then extending that, the third scoop, we've got 30 possibilities. So this is really, this is it. This is the solution almost. We do need to take into account the fact that this treats these three and however many more as if they're all different. And so we don't want to treat them as if we're different. So we've actually got however many possibilities here. We're wrong by that factor, that times that many. So we need to figure out, given my choices, say, vanilla, chocolate, library flavored, what was that, liver flavored, how many different ways can we organize that? Because that's how much we're out by a factor of that. Okay, so now we'll look at that. So let's say I've made my choice of 3 different flavors. How many different ways could I, or how many different ways could have gotten that in? Well, let's see. Well, the first flavor, okay, there's 3 possibilities. It could be vanilla, chocolate, or liver. Okay, but the next one, each of those, there's 2 possibilities. I mean, that vanilla could be matched with a chocolate, or it could be matched with a liver for the second possibility. And same here with the chocolate, it could be matched with a liver or a vanilla. Okay? And then the liver, it could be matched with chocolate or vanilla. So we've increased the number of possibilities. Okay, but after that, we've only got one choice, and so really it doesn't change. So this 6 here, this 3 times 2 has really done it. But for completeness, we'll put in the 1, because once we've got this, then each of these, you can see that after vanilla, chocolate, we've only got one choice left. Okay, so I won't list them all here. So what do we have here? We've got 3 times 2 times 1, which in this scenario, okay, I'm going to write it down here. 3 times 2 times 1. Okay, now we've got a shorthand way of writing that, because this is the kind of thing we see a lot of, and that is 3 factorial. Now, 3 with the exclamation point, which I always kind of want to read it as 3 or 3. All right, and that just means 3 times 2 times 1. So if I had 32 factorial, okay, that would be 32 times 31 times 30 times 29 times 28 times 27. Okay, so that would be overdoing it. But now we do have a problem of, how do I represent this little bit of the factorial? And I just gave a hint of it, because this is overkill. This is 32 times 31 times 30, but then times 29, 28, 27, all the numbers all the way down. So we over multiply when we do this, and so we need to unmultiply some of that. Okay, what's unmultiplying? We're going to divide. So if I've got 32 times 31 times 30 times 29 times 28 times 27, I want to get that 29 times 28 times 27. I want to be able to remove that. So I will just divide by the 29 times 28 times 27. And there you have it. Okay, so this will give me all of the ways that I can choose 3 different ice cream flavors, where order doesn't matter. Okay, out of a choice of 32 buckets of different flavored ice cream. That's it for the 32 3 scoop example. Now again, we want to generalize this. So what did I have here? Well, on the top, I've got n factorial, which we're overdoing it. Okay, now, and then on the bottom, I've got, I'm going to describe this next one here. How do we get 29? What's our general case? Well, remember, we've got 1, 2, 3. The number of terms here is k. So we want 3 less, or k less than n down here. And so that's what we're going to do, n minus k. factorial. Okay, so now we've generalized this. And now what we've got here is this is the number of what we would call permutations. Permutations, because what that means is order does matter. Okay? Like for example, let's say you've got a combination lock and your combination is 39, 24, 26 or something like that. Okay, putting that in a different order is not going to open the lock. Okay, so order matters with a combination lock. So strictly speaking, it should be called a permutation lock. Okay? What we've got here is a permutation, but because order matters, what did we put down here? Or I should say order doesn't matter. We have to divide by k. And this, it's so important, we will put it in a box. This is the result we were looking for. So I would suggest that you take this and try an example, and I guess I'll do the example in green. Okay? Kind of indicate that we're kind of on something else. So here's the question. Put the question over here. Take this home and try it, kids. Okay, so we've got a lottery, and you choose 6 numbers. Okay, out of 49. So when they draw the ticket, when they draw the numbers, they're going to have 49 balls with numbers on them from 1 to 49, and they will draw 6. And so by necessity, because they're not going to put any back, then they're all going to be different. Okay, and likewise, order doesn't matter. Okay? So if you choose the numbers 1, 2, 3, 4, 5, 6, which is just as likely as any of the other combinations, and they draw 6, 5, 4, 3, 2, 1, you still win. Okay, so you win big. Okay, so the question is, okay, so I'll make that point. Order doesn't matter. Okay, and they're different numbers. Maybe put that in there. Diff. 6 different numbers. Okay, how many possibilities? Okay, and your possibility of picking the right one is going to be 1 divided by a big number. Okay, so there's your homework where you can practice this. And now I'm going to go eat some ice cream, I guess. Like, comment, share, subscribe, do all that stuff. And in another video, the idea is that we're going to apply this to something that actually doesn't really look like it deserves it, but it'll be to demonstrate a mathematical theorem which we need for our trip to the Basel problem.